Greetings. Let us continue with the numericals on deflection of the determinate frames. Numerical number 3. Find the vertical deflection of the truss at a joint C shown in figure. Parenthesis in the bracket says the cross-sectional area of the members in mm square. Take E is equals to 2 into 10 raised to 8 kilopascal. The given frame is a part truss of 4 bay of equal width 5 meter and height 5 meter. Areas of the individual member has been assigned in parenthesis. It is interested to know what is the deflection caused at the joint C due to the applied loading. First, we'll try to find whether the structure is statically admissible or not. For that, we'll begin with the count of members. If you have count of members, it comes to be 13. If you have count of number of unknown reaction, it comes to be 3. And the count of joint, if we have about this member, it is about 8. If we put this in a static equation, ds equals to m plus r minus 2j, it results into a value 13 plus 3 minus 2 into 8 equals to 0, means it is statically admissible. Now we'll go with the finding out the unknown reactive forces by applying static equilibrium equation to the global frame. For that, we'll apply static equilibrium equation along the horizontal direction. Summation of force in horizontal direction yields to be ha minus 0 equals to 0, ha equals to 0. Now if we go towards the part of summation of forces in vertical direction, then we have a relation Ra plus Rb going upward minus 100 three times here, three vertically downward moving loads. This result in the relation Ra plus Rb equals to 300. I will apply summation of moment about the joint A. I will take the twist of all the forces about the joint A. So Rb into 20, the total span is 4 into 50, 20. It will have anti-clockwise twist, that's why negative, minus 20 into Rb plus 100 into 5, the load at the joint G, 100 into 5 clockwise twist, and at joint C it will have a twist about 100 into 10, and at joint H the force will have a twist about 100 into 15, resulting into a value Rb equals to 150, and from back substitution of this value in previous equation result into Ra equals to 150 kilonewton. Now I will begin with the force analysis in the member. I will find out the force carried by the individual member under the application of the applied loads here. To begin with, this will have a joint by joint analysis. I will select joint A. Here, if I prepare free body diagram from joint A, we will get four forces here: Ra, Ha, the reactive forces, and the member forces Fad, Fag. The direction of the members forces will be considered in such a manner that they are going to counterbalance the effect of the applied force. So here Fad is considered to be moving downward to counterbalance the reactive forces going upward. The component will have a counterbalancing of this, whereas Fad is going component in horizontal direction will balance the force in the member Fag. If I apply summation, if I go to the analysis here, let us first find out the what is the angle here, theta. So theta can be find out from the geometric relation. If I take a tan inverse of the product here, dg upon ga, means the vertical height versus the horizontal height, it will be 5 by 5 equals to 45. Theta works out to 45 degree. I will substitute this value and find out the relation with reference to forces in vertical direction. Ra, it is going upward, minus, consider this as a minus, Fad sine of 45, vertical component of this Fad force going downward. And this result into Ra value, Fad value as a Ra divided by sine 45 degree, which equals to 150 divided by sine of 45 degree, resulting into 212.13 kilonewton compressive in nature. Similarly, if I apply vertical horizontal forces equilibrium, then I will get Fag minus Fad cos of 45 degree. Ha is 0, that's why I am not considering here in the equation. This result into a value of Fag equals to Fad cos of 45 degree comes to be 150 kilonewton tensile in nature. I will mark these forces on the diagram so as to have ready reference for the next joint. Now I will move to the joint number, joint G. If I prepare free body diagram, there are four forces here, from which Fag and 100 kilonewton is known to us. One is applied force, and one we have got from the previous analysis. What remains here unknown, Fdg and Gc. If I take summation of forces in horizontal direction, it will be Fgc minus Fag equals to 0, Fgc equals to 150 kilonewton tensile in nature, Fdg minus 100 is equals to 0, result into Fdg is equals to 100 kilonewton tensile in nature. I will put these two forces in the picture for a ready reference. Now next joint will be joint D. If I take a free body diagram of joint D, we have four unknown forces here, Fad, Fdg. We have already calculated with reference to previous calculation part. Fdg, Fde is the unknown here. So if you apply summation of forces along vertical direction, we'll get Fad sine component, the vertical component of this force, minus going upward, that's a positive, minus Fdc sine of theta is going downward, that's why negative, minus 100 dg is going to be downward, that's why it results into a relation Fdc is equals to 70.71 kilonewton tensile in nature. If I move with a summation of forces in horizontal direction, I will get a relation minus FDE plus FAD cos of 45 degree plus FDC cos of 45 degree. Both are moving in upward direct, sorry, towards the right hand side, and these are moving towards the left hand side. That's why FDE results to be 200 kilonewton if I substitute the values related to FAD and DG in the equation. Now I will move to I will put these values on the figure here for a ready reference and move to the next joint, joint E. If I take free body diagram of joint E, FDE, FEF and FEG, these are the three forces which are not known to us. So what I will do, I will apply a summation of forces in horizontal direction. We will get a relation here, FDE minus FEF equals to 0. So FDE is equals to FBF, which we know as a 200 kilonewton compressive nature, whereas there is no vertical force to balance this component will yield to zero value if I take summation of force in vertical direction. So I will put this value on the picture here for a ready reference, and I will move towards the next joint, that is a joint C. If I go towards the joint C, there are four forces here. FCF and FCH is unknown to us, whereas FDC and FCG we have calculated from the previous statics. Now I will apply summation of forces in vertical direction. What I will get here, vertical components of these two forces, FDC cos sine of 45, FCF sine of 45 minus 100 will be the relation. If I substitute the individual values here, we can get FCH is equals to 50 divided by sine of 45 degree, which comes to be 70.71 kilonewton tensile in nature. Now I will take summation of forces in horizontal direction. I will the components here, FDC cos of 40 theta is going towards your left hand side, FCF cos of theta is going towards the right hand side. They are going to counterbalance each other, whereas FCH and CH will be GCH will be there, and there will be equilibrium between these two. They will be equal in magnitude but opposite in directions here. So it results into a value FCH equals to 150 kilonewton tensile in nature. Now I will put this values on the figure and move towards the next joint, joint number H. If I analyze joint number H, free body diagram work out to be here, four forces. FCH is known to us, 100 kilonewton is applied load. F and FHB is not known to us. If I apply summation of forces in vertical direction, what I will get? Minus FCH, sorry, summation of forces in x direction minus FCH plus FHB is equals to 0. That's why they will be equal in magnitude but opposite in direction, 150 kilonewton. The nature will be tensile. If I go towards the vertical forces, it will be FH minus 100. So it result into FH equals to 100 kilonewton. I will mark these forces in the picture and move to the next one, joint B. If I prepare a free body diagram of joint B, it results into FFB. There are two unknown forces here, FFB and FHP. RB is the force, reactive force coming upward. If I apply summation of forces in vertical direction, we get a relation FFB cos of 45. The vertical component of this, sorry, it should be sine of 45. Refer it as sine of 45 minus 150. If I put the relation here, FFB will work out to be 212.13 kilonewton. Whereas if I move towards the part of horizontal direction, FHB minus FFB cos of 45 degree, this we know that there is a balance between this force and resulting is 0, means there is a compatibility in the analysis. Now I'm interested to know about the unit load contribution, because what we say for analysis of finding out the displacement at particular joint, we are going to apply unit load at that particular joint, and we'll see the distribution of that unit load force among the members. For that we'll do with the analysis here. So we can write here RA equals to RB equals to 0.5, because we know that there is a symmetry in the loading, and we can write directly reaction will be equally divided among the two ends. So RA equals to RB. Now I will start with the joint by joint analysis to know the coefficient of the unit force distribution. So if I take free body diagram of a joint A, we will have RA and HA. Read this as a RA and HA. And here KAD is the member force from member force AD going downward, compressive in nature, and KAG I am considering is being in tensile nature to counterbalance the effect of the applied forces. Now if I apply summation of forces in y direction, we will get a relation minus KAD sine of 45 degree, the vertical component plus 0.5 reactive force. It will result into KAD equals to 0.7071 kilonewton compressive in nature. If I apply summation of forces in x direction, we will get minus KAD cos of 45, the horizontal component of this force, plus FAG equals to 0, resulting into KAG value equals to 0.50 kilonewton tension in nature. Now I will mark this on a figure and move towards the next joint, joint G. In joint G, we have three forces here, KAG, KGC are acting on a horizontal axis, whereas KDG is on a vertical axis. If I apply summation of forces along horizontal axis, it comes to minus KAG plus KGC equals to 0. it result into a value kag equals to kgc equals to 0.5, whereas there is no vertical component to balance this member force. That's why the member force will be here 0. So we can say it is 0 force member, whereas this will be having a, 0.5 tensile force in the member gc. Now I'll move to the next joint D. If I take a free body diagram, we have four forces here. If I apply static equilibrium equations towards this free body diagram, we get a relation. Summation of Fy results into Fad sine of 45 degree minus KDC sine of 45 degree. We can say from this relation KAD is equals to DC, which equals to 0.707 kilonewton tension, because already we know the value of KAD. Now summation of force in x direction result into FKAG cos of 45 degree plus FKD cos of 45 degree minus KDE cos 45, it will become twice the cos of 45, resulting into a value KDE equals to 1 kilonewton compressive nature. Now I will put the values here and move to the next joint E. At joint A we have three forces here, KEF, KDE and KEC. If I apply summation of forces in horizontal direction, we can get minus KDE plus KEF equals to 0, resulting into value KDE is equals to KEF, which equals to 1. And if I apply vertical forces here, it will be minus KEF equals to 0, means the member force in EC member will be 0, because there is no vertical force to balance the member force here. So that's why we will have here 0 1 the value. Now if we know that there is a symmetry in the loading, that's why there should be symmetry in the forces in the member. So what I will do, I will just replicate the forces here from the first joint towards the other unknown here. From the symmetry we can say force in FB will be, member FB will be equals to force in member AD, force in member BH will be equals to force in member AG, HG will be equals to GC, and here CF will be equals to the CD1. So if I take a symmetry here, the forces will be like this, and the member force FH will be 0, because if you take a symmetry here, this vertical member is carrying 0 force, this will also carry a 0 force, because there is no vertical component to balance the force in the member. Now after doing this, I will tabulate the result in a table format, where we'll have the columns like member, length, area, AE, product, FI, KI, FI, KI, LI, and Fi KI divided by E. Since the area of the members are different, length of the members are different, we are going for a additional columns as we have done in the previous cases. If I talk about the member AD member is a top chord member, and it is inclined in position. The horizontal distance is given to us 5 meter and vertical height is given to 5 meter. The length work out to be 7.07 meter. I have written in terms of mm here, 7070 mm. Area is known to us 4000. E is given to us in kPa. I converted that into kilonewton per mm square, work out to be 200. Then I have taken product here, and I have taken in terms of 10 raised to 3. It comes to be 800. Fi force we know from the F analysis. I have put that force, if it is compressive nature, it will be positive. If it is a tensile nature, I have put it as a negative. Similarly, Ki forces, we know the contribution of unit force among the member, so I have put that forces as a positive if they are compression, and negative if they are in tension. And then product of these three columns, Ki, Fi, and your Li. So it comes to be 1064.82. I have converted that into 10 raised to 6 format. Okay, divided and then divided with the column product AE here. So Fi, Ki, Li divided by AE will be there. The sequence I have maintained here, AD, I have taken all the members in top chord, then I have taken members in bottom chord, then vertical members, then I have taken the forces in inclined bracing, and then what I have done at the end, I have taken the summation of all the product. It comes to be 8.994, and this 8.994 is results into a displacement value which we can say as a diabas CV. If I write it a VC की जगह हम if I take it as a diaba equals to CV, then I can say it is a vertical deflection at the joint CV, which will be summation of Fi Ki Li divided by E, which comes to be 8.994 mm. That's, we can say that the deflection at the joint C due to the applied loading is about 8.994 mm. So with this I will stop the lecture here, and we'll continue with the next numerical in upcoming lecture. Till then, stay at home, be healthy. Thank you.